Welcome to your tutorial on Z-scores. I'm Dr. Lorianne Stretch, and I'm with the University of the Cumberlands. So all of this is based in normal distribution. So when we're talking about normal distribution, it's really important to understand that the bell-shaped curve represents what we mean by normal distribution. And with a normal bell-shaped curve, we have a very predictable way that data falls when we pull a sample from that population. And so if we choose to use a random sample from any particular phenomenon, we should theoretically get a normal bell-shaped curve. And the characteristics of a normal bell-shaped curve are that it is symmetrical, that the left is equal to the right with 50% of the data on both sides, and the mean, median, and mode are down the center of it. So you can see that the higher portion of the bell-shaped curve contains more data points. So you've got to think about this bell-shaped curve being filled with data points underneath it. And so we have this principle called standard deviation, which represents the average dispersion of the data from the mean. And with a normal bell-shaped curve, 68% of the data falls between -1 standard deviations to +1 standard deviation, always, every time. And 95% of the data is going to fall between -2 to +2 standard deviations from the mean. And 99.7% of the data will fall between -3 and 3 standard deviations from the mean. So you can see there's this very predictable way in which the data is going to fall. Now, with Z-scores, they're actually aligned with standard deviation. So a standard deviation of -1 is a Z-score of -1. A standard deviation of -2 is a Z-score of -2, and so on. And so these are aligned. Standard deviations representing the average dispersion from the mean, and Z-scores are the number of standard deviations the raw score is from the sample mean. So let's take a look at some definitions here. So again, Z-scores represent the number of standard deviations from that the raw score is from the mean. So Z-score is a standardized score. So it takes a raw score and it standardizes it using standard deviations so that we can then compare that single value to a sample mean or a sample to a population. Why do we do this? Well, one, it represents where the raw score falls on that horizontal axis, the x-axis, and we use it in relation to standard deviations. It standardizes the score so we can compare it so that things like sample size, even the statistical analysis that we might have used, none of that is going to impact it, right? It's a standardized process that we can compare. It also determines the probability or even the percentage of the score in an existing data set. And we're going to get to play with that a bit today as we go through this tutorial. So why do we even need these, right? Well, here I have an example for you of two sets of NCE scores, the National Counselor Exam scores. One of these sets of the scores represents the NCE average scores for all CACREP accredited programs. And the bottom one represents the specific NCE scores of a particular university. And here you can see that the total, the top row, represents the total number of questions that were on each area of the NCE. And of course, these areas are abbreviated, but they align with the CACREP standards. So we have human growth and development, social cultural development, helping relationships, group work, career development, assessment or appraisal, research program evaluation, and professional orientation and ethics, with the total number of questions being represented in the far right. We have the US mean. So this was the mean score across CACREP accredited programs for each of the areas. The standard deviation for the United States. And then on the bottom two rows at the top is for the actual K-CREP accredited program. So the first two rows that say US, that's for everybody in the US that took the NCE, K-CREP or not. And then the bottom two rows of the top chart are the mean for K-CREP only accredited programs. So we'll be using this later to calculate Z-score. But right now you can see it looks like, for example, the K-CREP accredited programs scored better than the US mean in human growth and development. Same thing for social cultural. Now, if we look down at the university scores, we can again see the number of questions, the US standard deviation mean, you can see that's the same as the top chart. And then we have the mean for this particular university, which does happen to be a K-CREP accredited school. And you can see the means of each of the areas and the standard deviation. So the way to think about this is the population is the US population. So all the US, everybody who took the NCE at that time that was in the US. And then the next sample is the K-CREP accredited programs. And then an example of that sample, like a data point within that sample, would be the university. So initially, it looks like I should be able to compare these and see if there was a difference. I can show that there's a mathematical difference, but I don't know if that mathematical difference is significant. Significant means that it's likely to be because of what happens at that university, or because of what happens because you're a K-CREP accredited program, and not just because of chance. I can't determine that based off of what's happening here in these charts alone. I would need to standardize the scores so that I could compare the scores to see if there's a significant difference in those scores. We'll do that a little bit later. For now, let's look at what Z-scores can do for us. So we need the Z-score formula. So to calculate a Z-score, we're going to take the Z-score and we're going to look at the raw score or the sample mean, and we're going to subtract that from the population mean and divide it from the population standard deviation. So all of those are described for you here. A Z-score of 0 indicates that the value is exactly at the mean. Remember, a Z-score is aligned with the standard deviation. If we have a standard deviation of 0 or Z-score of 0, that means it's sitting at the mean. A positive Z-score indicates that the value is above the mean or to the right of the mean. A negative Z-score indicates the value is below the mean. And the magnitude of the Z-score shows how far that value is from the mean. So the number, as it increases, is going to be further and further away from the mean. So let's look at an example. So we're going to be looking at council workload. The average number of clients seen by a counselor per week is 25 with a standard deviation of 5. So we're saying that this is the average for all counselors. So this is the population. What percentage of counselors see at least 30 clients per week? Using the formula that we have for Z-score, we're going to plug in the sample Z-score, which in this case is going to be 30 because that's what we're trying to figure out, with the population mean of 25 and the standard deviation of 5. We're going to calculate that. 30 minus 25 is 5. We're going to divide it by 5, which gives me a calculation of 1. So we have a Z-score of 1. Now, there's a chart, the statistical tables, which is linked in the assignments and in our classroom, that I could look it up. Now, I happen to already know that a Z-score of 1 aligns with the standard deviation of 1. And I know for a fact that 50% of this chart to the left of the mean is 50% of my data. I also know that because there's 68% of the data between the first two standard deviations, and that when I divide that by 2, that's 34, right? So actually 34.13 if you want to be exact. So I can take 34.13 plus 50%. So I'm looking at this part of the data here. So this would be 50%. And the part between the mean to this first standard deviation is 34.13%. So I add those two up and I get 84.13% of the data. So what I'm saying here is that a z-score of 1 corresponds with a percentile of approximately 84.13%. Therefore, about 100% to minus 84.13% equals 15.87% of counselors see at least 30 clients. Because I wanted to know what percentage of counselors see at least 30 clients. So when I look at where this point is, this x equals 30 and z equals 1, that's representing 30. So to know at least 30, I need to know 30, 31, 32, 33, 34, 35, etc. So I need everything to the right of that mark where the x equals 30 is to understand which counselors see at least 30. Everything to the left of that is going to be 30 and less. I hope that makes sense. Let's go to our next one. Counselor workload, again, same setup. 25 is our population mean, standard deviation of 5. What is the number of clients seen per week that marks the 20th percentile of this distribution? Now, I've reworked this formula a little bit. It's the same formula we had before. You can see that down here. So I just took the z equals x minus mu divided by standard deviation, and I isolated the x. So to do that, I had to multiply both sides by the standard deviation, which is how I got this z equals the standard deviation. And then I had to add mu to both sides, the population mean, and that isolated my x, which is how I got this formula. I'm going to use the statistical table. I have a screenshot for you on the left, and I'm going to look up inside the table, the negative table. Why do I know it's the negative table? Remember, let's go back here to this, that when I'm looking at a normal distribution, this is basically 0 over here. And then I'm going to go 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, and beyond. All right, so I'm going to distribute this equally among that, and I can see that my lower percentages are here, up to 50 at the mean, and then above 50 is going to be to the right of the mean. So that tells me that the 20th percentile is going to be to the left of the mean. And since that's true, I'm going to use the negative table, which you can see z negative, because if my number is on the left side of the mean, it's going to be a negative z-score. And I'm going to try to find the 20th percentile here. And so the percentages are in the middle. These are actually listed as proportions. To make them percentages, I just multiply each one of these by 100. So if I see 0.0003 and I multiply that by 100, it's going to be 0.03%. Whereas this one right here is going to be 1151. It's going to become 11.51%. So if I multiply by 100, I'm just going to move that decimal over to the right twice, and I'll have a percentage. If I move it back 2 places to the left, I have a proportion. So when I search this table, I'm going to look down each row until I find the 0.2s. I found the 0.2s. This is 0.21, 0.20, 0.26, 0.203, 0.205. And this is the closest number that I can get to 0.2. So that's the number I use. And the way I read the z-score is first I look to the left, negative 0.8. And then up here, I get the 100th number, which is 4. So that's going to give me negative 0.84. So you can see I plugged that into the formula here. So x equals 25 plus. I calculate this because of the order of operations first. So negative 0.84 times 5 equals negative 4.2. I subtract that from 25, and it gives me an x of 20.8. What does that mean? So what that means is the 20th percentile is approximately 20.8 clients per week. And you can see I've drawn that out for you and estimated where that is. How did I know that the line was here? Because z equals negative 0.84 is going to be between the 50th, the 0. Just remember this line right here in the middle is going to be the, is going to be the 50th percentile, or z standard deviation equals 0, and this is going to be one standard deviation to the left of the mean. So that's going to be a standard deviation of -1, and a z-score of -1. So negative 0.84 would fall to the right of that. All right, next one, same workup with the population of 25 mean population. The population mean of 25 with the standard deviation 5. What is the proportion of counselors who see between 20 to 30 clients per week? So I'm going to use the Z formula for the 20 clients. I'll calculate 20 minus 25 divided by 5. That gives me a -1. And for 30 clients, that's going to give me 30 minus 25 divided by 5 equals 1. Now I can use the statistical tables, the negative table for the -1 and the positive table for the 1, or I can remember that 34.13% of my data falls between one standard deviation and the mean, and I can add those up and get my 68%, but we're just going to do it through the manual way of looking at the charts as well to see if that's true. So I'm going to go down the negative chart, and it's going to tell me that negative standard deviation or z-score of -1 is a proportion of 0.1587. And if I go to a positive z-score of 1, it gives me 0.8413. Now remember, this isn't the full answer. This is just telling me what the proportions are represented at those demarkers. So when I go here, you'll see my normal bell-shaped curve. I know that between -1 and Z1 is 68.26, but if I want to really figure it out, I plug in, okay, this area from the right bar all the way out is 84.13. And from the -1 standard deviation to the left is 15.87. What I can do is take this number, the 84.13 minus 15.87. It's going to give me the 68.26%, leaving me with an interpretation that a z-score of -1 corresponds with a percentile of approximately 15.87, and a z-score of 1 corresponds with a percentile of approximately 84.13%. Therefore, the proportion of counselors seen between 20 to 30 clients per week is 84.13% minus 15.87% for a total percentage of 68.26. Next problem, what is the percentage of counselors who see between 15 to 35 clients? Now, in this particular formula or problem, I use my formula and I realize that for 15 clients, it's -2. And for 35 clients, it's 2. Now, I already know that the amount of data that is between -2 to 2 is actually 95%, but let's check it and make sure. So using my negative chart, I'll go down to 2. That's going to give me 0.0228. I can multiply that by 100, and that's going to give me 2.28%. And for the +2, same thing. I'm going to go down here, find +2. 0.9772, which is with a percentage 97.20 or 72. Because the reason I'm changing it is because it's asking me for the percentage. If it asks me for the proportion, I just leave them as proportions. When I plot that on my normal bell-shaped curve, I have my numbers here. X equals 35. I know it's at this little marker because it's the second standard deviation, which is aligned with the second z-score. And same thing here. And if I want to do this manually, I plot how much distance or data is included in the z-score of 2, which is 97.72. And for the -2, it's 2.28%. I can subtract those and I end up with 95.44%. So again, same thing, z-score -2 corresponds with the percentile of approximately 2.28%. A z-score of 2 corresponds with the percentile rank of approximately 97.72. Therefore, the percentage of counselors who see between 15 to 35 clients per week is 97.72% minus 2.28%, which equals 95.44%. Next problem. Suppose you randomly select a counselor who sees 40 clients per week. Calculate the counselor's z-score and interpret it. What does it tell you? So using my z-plet formula, I'll calculate my z, which is a 3, and then I'll look at the table. And again, it just gives me 99.87 Not surprising, because I know that when I have anything between 3 standard deviations, at 99.87% of the data is going to be at that point. So I'm going to plot this. Now remember, we're looking for this 40 here, right? So we're looking at the 40 and we want to calculate it. So this is saying anybody who sees less than a 40 clients, that's 99.87% of the counselors. Only 0.13% of counselors see 40 or more. So I'm going to interpret this as using the z-table. A z-score of 3 corresponds to a percentile of approximately 99.87%. And this tells us that counselors who see 40 clients per week is in the top 0.13% of the distribution, indicating a very high workload. Next problem. What is the probability? Note the change in language. We've moved from percentages to probability of randomly selecting a counselor who sees 18 clients or more per week, or more. So that tells me I'm going to want to see what the percentage is to the right of that 18 as a z-score. So, or as a raw score that I convert to the z-score. So let's take a look at our z-score formula. We take 18 minus 25 divided by 5. So we're actually going to calculate what's in the percentages in the parentheses first. So 18 minus 25, we calculate that, then we divide that by 5, and that gives us negative 1.4. Negative 1.4. So I'm going to look at the negative chart, and I'm going to find 1.4 in the negative, and it's going to tell me that it's 0.0808. I'm not going to convert this to percentages because it asked me for the probability. Of course, I did convert it to percentages, so it shouldn't be converted to percentages. It should be portion. So I should have left this as 0.0808, and this should be 0.9192. I see even Dr. Ellie makes mistakes. And then I have x equals 18 with a z-score of negative 1.44. I know that that's falling between this z-score of 1 and the z-score 2. And I say using the z-score table, a z-score of negative 1.4 corresponds to a proportion, because it asked us about the probability, of approximately 0.0808. Therefore, the probability of randomly selecting a counselor who sees 18 or clients or more per week is 100 minus 8.08% equals 91.92%. I would actually keep that as proportion, which would be 0.9192. So to summarize the steps, first we have to understand the problem. What is the population mean? What's the standard deviation mean of the normally distributed data set? Then I'm going to determine the specific value or range of values that I need to calculate the percentage of the proportion. Then I'm going to calculate the z-score using the formula for z-score. Z equals the raw score minus the population mean divided by the population standard deviation. If I'm given a specific value of x, I'm going to substitute that formula to find the z-score. For ranges, I'm going to calculate the lower and the upper bounds of that range. I'm going to use my z-table to find the corresponding percentage or percentile, and I will provide the area of the curve to the left. So any number I look up in that chart is going to give me the value or the area to the left of that number or value or z-score. I'm going to interpret the percentile for values that are greater than a mean. I expect the percentage points to represent the data below that value or to the left of the value. For values less than a mean, I'm going to subtract the z-score from 100%. I'm going to calculate the proportions for ranges, looking at the upper and the lower bound. And then I'm going to draw and shape the normal bell-shaped curve and figure out what part of the data I need and subtract or determine appropriately. Let's go back to our original example. So why was z-scores helpful here? So for this, you can see I've color-coded this using the z-score formula. So you can see that the z-scores are in orange. I've added that row. And then the raw score is the x, or the sample mean, which is in blue. The population mean is in purple, and the population standard deviation is in red. So what I did in the first column for the K-CREP accredited programs is I took the 7.56, which is the mean of the K-CREP programs for human growth and development, and I subtracted the mean of the US population, 6.66, and then I divided the population standard deviation of 1.88, which gave me a z-score of 0.48. I repeated this for each one of the areas, including the total, and I did the same thing for the university. And now, and only now, can I actually compare the K-CREP accredited programs with this one university. How did this particular university, this particular K-CREP university, do in comparison to the K-CREP accredited programs? So for example, for human growth and development, this university was 0.21 standard deviations or z-score from the mean, whereas the K-CREP programs as a whole were 0.48. So this tells me that this university still did better than the United States average mean for human growth and development for this particular test administration, but not quite as well as all of the K-CREP programs in totality. For social cultural development, same thing is very similar. You have 0.31 for the university, still better than the mean average for the United States sample, but not quite as good as the K-CREP accredited programs as a whole. And you'll see that pattern is pretty consistent throughout the rest of the scores. So this can give you an idea of, like, if you were to draw this out in a normal bell-shaped curve, how that would look and where the K-CREP scores would be in comparison to this particular university's program, which, by the way, is not our university, but a different university. Want some additional practice on this? Then I encourage you to look at the research study on counseling session duration and client satisfaction that's in the counselor guide from pages 159 to 164 for some additional practice. Please think about any questions that you may have, bring those to lab or to class, and we will talk to you soon.